My name is Nick Stasulis, and I'm a hydrologic technician with the main office of the New England Water Science Center. In this screencast, I will discuss the basics of reviewing extrapolation methods for midsection measurement data collected in Section by Section Pro. It's important to note that the USGS Extrap program cannot be used to evaluate extrapolation methods in midsection software. It is a manual process, as we'll discuss. When evaluating extrapolation methods for any ADCP data, it is useful to have some knowledge of the site conditions to aid in your understanding of an appropriate extrapolation method. For example, it's useful to know about the bottom substrate type and size in relation to the channel depth, the channel shape, and hydraulic features upstream and downstream of the cross-section. Certain channel shapes can tell us something about what the expected velocity profile might be, as we see in this diagram from Chow. It shows that some site conditions might cause us to expect a bend back at the surface, indicated by the blue arrows, while some might cause us to expect an increase in velocity towards the surface, indicated by the red arrows. Also, the roughness of the bottom could tell us something about the expected power exponent. At this site, there are large boulders on the river bottom in the manned cableway section, and we would expect this to cause a bend towards zero on the bottom, higher in the water column than the standard power curve. Also, this increased friction is expected to cause a higher exponent, as the rougher the bottom, the higher you would expect the power exponent to be. In this data set, we can actually see in the contour plot that velocities decrease near the bed in nearly every station due to those large boulders on the stream bed. Your evaluation should begin by scrolling through each vertical using the playback controls or by hitting the Control left or Control right arrow keys. While scrolling, look at the velocity profile plot and evaluate how the green top fit and orange bottom fit line up with the measured data shown in red and extend beyond that data into the unmeasured areas. The blue line represents the power fit, but remember that the software will always use the measured data in red where it exists. In the plots, look for consistent trends of measured data and the extrapolated areas not agreeing. And if there are consistent differences, it's likely a change is needed from the power default. In this data set, we do notice the data on the bottom going towards zero higher in the water column than the standard power fit, causing a large difference between the measured data and the bottom extrapolation. If a change in slope to the measured data will help align the extrapolation, it may be as simple as increasing or decreasing the exponent. A lower exponent will cause a vertical profile due to a smoother bed, while a higher exponent will flatten the profile due to a rougher bed. The power exponent is changed for the entire measurement in the processing dialog. If the exponent alone doesn't allow a proper fit, you might need to change the method as well. The method can be changed for each individual vertical when appropriate. The wind-driven method uses constant no-slip and will take the uppermost bin and carry that velocity to the surface and fit a power curve through the lower 20% of the data. It is important to note that you can and should change the exponent for the no-slip method if the standard exponent doesn't follow the trend of the measured data. Remember that the exponent can only be changed for the entire measurement in the processing dialog. In this example, we see that constant no-slip with the standard exponent doesn't define the shape of the measured data very well, but an exponent closer to 0.39 shows a much more reasonable shape, as would be expected in a cross-section with rougher than typical bed. The bidirectional method uses a 3-point on the top, fitting a line through the top 3 bins, and a no-slip on the bottom. 3-point is useful in conditions where strong winds cause a severe bend towards zero on the surface. Use of this method should be confirmed with detailed field notes. Note that in version 1.14, the bidirectional method does not work properly and should not be used. Use of the ice method utilizes a no-slip on both the top and bottom, and this method should only be used for ice conditions where velocities go to zero on the surface. Be aware that changes to the power exponent apply to the ice method, as it is using a power fit of 20% of the data on the top and the bottom. There is some trial and error associated with selecting the most appropriate method for the measurement. as some verticals, particularly on the edges and behind bridge piers, may show profile shapes much different than the main channel where the majority of the flow resides. After your evaluation is complete and you've selected the method that you feel is appropriate, there are a couple steps left. First, check the change in final discharge from the default power to the method you've selected. If the change is very minimal, say less than 1%, it is typically not worth additional consideration. If the change is quite large and uncertain, you might need additional examination, and downrating your measurement based on the amount of estimated uncertainty from the extrapolation method would be appropriate. Also, if applying a change, make sure that change is documented in the field notes.